Okay, now this parameter that we define, I mean, you will not see that parameter quite often, but that is a parameter that kind of interpolates between we had studied the completely inelastic collision, in which case this was just 0, and the other limit is completely elastic collision, and in that limit this parameter is just 1. And this parameter is always between 0 and 1. For a given collision, this parameter can in fact take any value depending on what are colliding. For example, if you are playing pools or bowling, this parameter in those cases where you have these very large solid objects will be more or less at the order of 1. So it is almost elastic collision. But for example, if you have two cars that are colliding, well, the cars are not that solid, so if two cars are collide, most of the time they will just stick together. If they stick together, this parameter will be very close to 0. It is just a parameter that is used to to parameterize the properties of the collision itself. And in general, it will change from collision to collision. You have some tables of this parameter for the collisions between different solid materials. So for example, if you drop some marble or some plastic ball on the ground, on wood, or on a rock, that you have the tabulated list of how much is this parameter, this one. Now, any other questions about all of this? Now, there has been some not so complicated, but boring with the algebraic manipulations, but the main idea is that you have the initial momentum, you have the final momentum. These two have to be equal. Of course, this is not enough to uniquely determine the final velocities. We need some additional input, and that can be, we might assume that the kinetic energy is conserved. This is an assumption, or that is the assumption that this parameter is 1. Or we might assume that the objects, they stick together after the collision. This is what we call the completely inelastic collision. In that limit, this parameter is just 0. Or we can just assume anything else. For a given collision, you can just say that, okay, maybe this parameter for that particular collision was 0.5. And once you fix this parameter, then that gives you a second equation to solve for the two unknowns. We don't know V1 prime, we don't know V2 prime. We need two equations. Conservation of momentum is just one of them. The second one is this equation over here. Of course, for a known parameter eta. Now, any questions?
Inelastic collision, it is relatively after the selected two mass, we are considering the center of mass.
Okay.
In our calculations. But if in other situations, if it is possible, we don't carry the center of mass, can we make it any calculation?
Well, you see, there is one thing. You cannot just ignore the center of mass. Whatever you do, the velocity of the center of mass doesn't change if there are no external forces. You cannot just ignore this. You have to take this into account. The velocity of the center of mass does not change, whatever the internal forces are. So if the two objects stick together, then the center of mass will be nothing but right at the position of the object. So both of the objects should be moving with the velocity of the center of mass. There's no other possibility there. You cannot ignore the center of mass. Ignoring the center of mass velocity is like ignoring the third law of Newton, which you cannot do. Any other questions? For? Well, you see, we didn't make any assumption about these objects, these masses. We have these two masses. They can be just like two pieces of chalk, or you can have, I don't know, two black holes, or two galaxies even. These laws are still valid in those cases. Of course, now we are considering only the one-dimensional case, or in astrophysical objects, they rarely move in one dimension. So we need to go beyond one dimension. So what happens in collisions when you have two dimensions? And also when we talk about collisions, they don't have to be just collisions like this. I was just mentioning in the break to one of your friends that, for example, we have these comets that approach the sun, and there are some forces between them. There will be gravitational forces which we will study. So there here is the comet, the sun will be moving, the comet just comes here, goes around. This is also a collision. Although the comet doesn't touch the sun. What we mean by collision is there are some forces over there that changes the velocity of the objects. And we know whatever the forces are, the momentum has to be conserved. Now you can apply the same principles here. Initially the comet is very far away. Maybe it came from, not from the solar system, but from some other galaxy, let's say. At this very far away distances, the comet has some momentum, the sun has some momentum. And then after it passes close to the sun, it will just go very far away where the sun will practically have no effect on it. So if they have some, the comet will have some momentum, the sun will also have some momentum. Again, the momentum, these two momentum have to be equal to whatever happens in between. The momentum conservation is independent of the nature of the forces that causes the momentum of each one of the particles to change. Whatever the forces are, as long as they satisfy Newton's third law, the momentum has to be conserved. Now let's look at this example. This question. Not question, but this example here. Now we have these two masses, the mass A and mass B. Let's first determine the velocities of the object. Let's start with the mass A. This is the initial velocity of this is the velocity of mass A as a function of time. In units, I already calibrated the units in kilogram meters per second, meters and seconds, so the velocity here is in meters per second. So what is the velocity of this object before the collision? Well, you see, by the way, here you already see that the collision is taking place somewhere over here. Now, what is the initial velocity of the object before the collision? What can you say? .6, 0.6. I would say 0.65 plus minus 0.05 to be on the safe side. Now so we have this first mass. Zero point 0.65 plus minus 0.05 meters per second. This is the initial. Let's look at the final one. This is the initial, Vx final. What is the x component of the velocity after the collision? It is somewhere, well, this line is 0.2. Let's say 0.2 plus minus 0.1. It is less precise. .2 plus minus 0.1 meters per second. Well, the mass is 48 grams, or 0.048 kilograms. So what is the initial momentum? X component of the initial momentum. So somebody who has a calculator. Nobody has a calculator? So it is more or less something like 0.03 kilogram meters per second, plus the error bars, of course. And if you have the calculator, you can calculate the error bars for me. And the final momentum it is, okay, it's this one, 0.01. Kilogram meters per second. Do you agree? Yes or no? Or you are just asking why are we multiplying those numbers? Okay. Now let's look at the mass B, the other mass we have. What are the velocities? X component of the velocity initially. Okay, what's the value of the initial velocity, x component of the velocity? 0. Well, you see, 0 is this line. I would say it's definitely negative. So it's something like minus 0.05 plus minus 0.05. The final velocity, this is the final velocity after the collision. It is 0.4 plus minus 0.05. Again, meters per second. The mass is the same. So what is the initial momentum? .02 meters per second. The final x component of the momentum .16 kilogram meters per second. Do you agree? So the final velocity is something like, yeah, 8 times the initial velocity, so the final momentum is like the 8 times the initial momentum. So what is the total initial momentum? We did some mistake somewhere, right? This is the initial momentum. I have one more 0 over here. Well, the initial momentum is more or less 0.03 kilogram meters per second. Well, this is very small compared to this one. So mainly, this only this one has the initial momentum. And the final momentum, if you just sum these two numbers, 17. So do we have some more mistakes somewhere? Where? P final is 0.02. Well, how do you get 0.02? It's 0.4 times 0.048. Yes, 0.02. And if you just sum them up, 0.03. So momentum is conserved. The x component is conserved. Now, any questions on what we have done here? Now, this is not just one-dimensional collision, by the way. This is two-dimensional collision. And we have actually seen that the x component of the momentum is conserved. Well, in two dimensions, we have the momentum is a vector, so it has the x and the y components. Here, this is the x component of the collision, which is conserved. Well, we will not repeat it, but the y component of the collision is also conserved. Now, let's look at the energy. Is the energy conserved? Is this an elastic collision or an inelastic collision? Let's try to determine that one also. Let's look at the speed of the A and the speed of the B. Now, of course, we know the x and the y components, so we can calculate the x and the y velocities. From that, we can obtain the speed. But it's nice that this program allowed me to calculate the speed directly. So you see, before the collision, of course, the speed has larger error bars. Now, this is where when the collision happens. So before the collision, this is where the speed is. So it's something like 0.5 plus minus 0.05. Initial, this is equal to 0.5 plus minus 0.05 meters per second. This is the initial speed. The final speed of the same mass after the collision is right over here, while it's on the average 0.4, again plus minus 0.05. Let's say VA final is 0.4 plus minus 0.05 meters per second. Oh, sorry, this is for the mass P. Now, if you look at mass A, this is the speed, how its speed changes. This seems to be more precise. Now, before the collision, it is 0.65 plus minus 0.05. And after the collision, is right over here, it is like something like 0.2 plus minus 0.05. Now the masses are the same of both of the pucks, so conservation of kinetic energy just implies that VA squared, the initial value of VA squared plus the initial value of VB squared should be equal to the final value of the speed of A squared, the final value of the speed of B squared. So is this satisfied or not? If this is satisfied, we know that the kinetic energy will be conserved. The kinetic energy is just 1 over 2 times the mass of the puck multiplied by these numbers. I can just cancel it from both sides. Okay, somebody with the calculator. You learned how to use the calculator finally. Yes, what is the VAI squared plus VBI squared? You calculate the final value. These are the initial. 0.117 meters squared per second squared. Okay, that is almost 7. Right? Without the 1. Okay, I know. 0.68 is approximately 0.7. If you round it, the final values. Somebody else? Okay, so this is what you obtained also, right? So, is this elastic collision or not? This is not an elastic collision. But the conservation of momentum doesn't depend on whether it is elastic or not anyway. Momentum is always conserved whether the collision is elastic or not. Now, of course, you have to put in the error bars over here. The error bars can be huge, can be large. For example, it is possible that this number is 0.7 plus minus 0.3. This number is 0.2 plus minus 0.3. That means this collision can still be elastic with the error bars. We didn't put the error bars. You can put in the error bars and see whether we are sure that this is not completely elastic or not. Now, any questions on what we did over here? This is just a real-life application of what we are discussing over here. I mean, although this video is not something I created, but you can just, if you have a smartphone or a camera, just collide two objects and see how they collide. And you can analyze it using this tracker. You can just download it from the web. And then see if it is elastic or inelastic, whether momentum is conserved or not. I mean, you can even roll two balls together. We didn't yet study rotations, but conservation of momentum is also independent of whether the balls are rotating or not. The rotation doesn't change the fact that linear momentum has to be conserved. Of course, the rotation might change, so it will change whether the collision is elastic or how much inelastic it is, but it will not change whether the momentum is conserved or not. Now, any questions here? Now, let's do this more formally. Okay, we have seen that this X component of the momentum in this two-dimensional collision has to be conserved. Let's look at the formal discussion. Let's look at what happens in collisions in general in two dimension. Now, what we mean here by collisions in two dimension is that you send one mass. Now, of course, this time they will have, the velocities will have a direction, so we have to use the vector notation. And now you have another mass, V2. Initially, we can say, well, these are just their velocities at any point. And something happens over here. We don't need to know what happens over there. But when they come out, the first mass has this momentum, has this velocity, V1 prime. It still has the same mass, M2, V2 prime. So you have these two masses, you send them to some region, and then they just come out from that region with different velocities, with different masses. It is possible that, for example, in the CERN, what we are actually doing is we are just sending two masses, one proton, another proton, into a region which we do not see. We don't really know what happens. We are just sending protons there. And when the protons collide, some particles just come out. It doesn't have to be protons. These two masses can be different. You can have more than two particles coming out. We can measure their velocities, and hence we can obtain their momentum. And still, the momentum of the initial particles that we sent is always equal to the momentum of the final particles that come out. This conservation of momentum is valid at every level of science we know. I mean, for example, F is equal to ma, we now know that in certain cases, we cannot really apply it. For example, if the objects are moving close to the speeds of light, it is no longer valid, but conservation of momentum is always valid. We have never observed any violation of conservation of momentum yet. Let's write the conservation of momentum for this system. The initial momentum will be just m1v1 plus m2v2. The final momentum is equal to m1v1 prime plus m2v2 prime. How many unknowns do we have in 2 dimensions? Why 4? How many unknown numbers do you have? Well, just like the previous case, we don't know the final v1 prime, we don't know the final v2 prime. But now these are vectors. They have the x component and they have the y component, none of which we know. So we have 2 unknowns over here, we have 2 unknowns over there. So we need 4 equations to solve for each one of them. Well, we know the conservation law, conservation of momentum. Pi should be equal to Pf. How many equations are there here? How many? 8. 8? Here? Well, 8 is kind of too much. How many equations do we have over here? 1. 1 is too small.
For the x and the y.
We have, for the x and the y components, we have 1 equation each. So this gives us 2 equations. So we know that the x component of the initial momentum should be equal to the x component of the final momentum. This we had already seen in one example. We didn't study it, but if we had studied, we would have seen that the y component of the initial momentum should be equal to the y component of the final momentum. Or in terms of the speeds, we know that m1 v1x plus m2 v2x should be equal to m1 v1 prime x plus m2 v2 prime x, and m1 v1y plus m2 v2y. This is equal to m1 v1y prime plus m2 v2y prime. Okay, we have 4 unknowns. Now we have 2 equations. We need at least 2 more equations to determine. Again, we can consider 2 cases, 2 limiting cases. Now, completely inelastic case, now this is the case when the 2 objects, they just stick together. Their relative velocity should be 0. This is how we define the completely inelastic case. v1 prime minus v2 prime is equal to 0. And so this gives us v1x is equal to v1 prime x is equal to v2 prime x, and v1 prime y is equal to v2 prime y. So if they are completely inelastic, they just stick together, and we have 4 unknowns, and we have these 4 equations. So we can uniquely determine what their final velocities will be. Of course, it will be their common velocity. They just stick together, they move together, and so that reduces the number of unknown velocities. And the other limit is completely elastic collision. In which case, the initial kinetic energy is equal to the final kinetic energy. How many equations are there here? 1 or 2? I is the initial, F is the final. 2 equations. This is just 1 equation. You see, this equation is a vector equation. So if you have two vectors that are equal, each one of the components have to be equal. That gives you a vector equation, in fact, represents more than one equations in terms of their components or in terms of numbers, not vectors. This vector equation just corresponds to two equations for the unknown numbers. But this is not a vector equation. This is just the relation between the speeds of the object. So this is just one. So in the completely elastic collision case, in fact, we have, these two equations, they're always there, they are conservation of momentum. But if we have a completely elastic collision, we only have one more equation. So it's not possible to determine which direction the objects move after the collision. In the case of the inelastic collision, we can determine their direction uniquely, but in the case of the elastic collision, well, they can just scatter in, I don't know which direction. So we need at least one more input to determine which direction the objects are moving after the collision. Without that input, we cannot say anything. Now, any questions up to this point? And in the homeworks, you will be solving some examples to see how these will work. But any questions about in general? No questions? Yes.
When two bodies collide, at the point of collision, I can assume that at the point of collision, there is a force acting on the two bodies. So I don't know the direction of the force, but I know the force of one is negative F of the other.
True.
At that point now, so I can see that using force for the first one will be M1 minus M1 V1 over T for the first one. And then M1 M2 V2 minus M2 V2 over T for the second one.
Now, why do you divide by T?
No, I will still remove the T eventually because it's the same time. I will still remove it.
Okay.
So in that case, we have M1 V1 minus M1 V1 equal to M2 V2 minus M2 V2.
Okay.
So in that case, how I want to understand why eventually is M1 V1 equals M1.
Well, this is conservation of momentum. This is the initial momentum we have over here. M times V is the momentum. This is the x component of the momentum of the first particle. This is the x component of the momentum of the second particle before the collision. This is their momentum after the collision. And we know that they have to be equal because momentum will be conserved whatever the forces are. Now let's go back to this example where we have these two masses. Now what is the change in the momentum of the first particle? Mass A. 0.02 kilograms meters per second. Mass A and mass B. Delta P of the A, the x component, is equal to, is it plus or minus? Minus. So because delta is the final minus the initial. But we had already seen that the change in the momentum can also be written as, well, in vectorial form, the force times the time it takes for that change to happen. Well, in fact, this we will call the average force. If we take the limit as delta t goes to 0, then this will be the instantaneous force. So we already know the x component of the change in the x component of the change in the momentum. So if we want to calculate the x component of the average force acting on the particle A, we just need to determine divided by delta t. Now we need to determine what delta t is. Now let's go back to our example. So here was the data we have. So if you look at here, the collision more or less seems to start at this point, at the time 0.4, more or less. And it ends somewhere over here, 0.5. So the time of the collision is 0.1 second. So delta t is 0.1 seconds. So the average force, the x component of the average force will be we have the 0.02 divided by 0.1, it will just give me 0.2. Minus 0.2 kilograms meters per second squared, or minus 0.2 newtons on the average, on the x direction, of course. Now this is the force acting on A. Of course, from this information we can also determine the average x component of the force acting on B. It should be plus 0.2. Well, let's check if it is actually the case. Now, the force acting on B, the average force, the x component will be the change in the x component of the momentum of B divided by delta t. So if we look at the change in the x component of the momentum of B, it is this one. This is the mass P, this is the final momentum, this is the initial momentum. The initial momentum is almost zero. It is almost vertical, moving vertically. If you look at this number, the x speed is almost zero, so this is 0.02 plus 0.02. 0.02 kilogram meters per second. The collision time is again the same, it's just 0.1 seconds. So it is 0.2 kilogram meters per second squared, which is 0.2 newtons. If this is positive. Well, this is nothing but the Newton's third law. These are the action-reaction forces. So here we have actually made a measurement of the validity of Newton's third law. The forces always seem to be forming action-reaction pairs, at least in this case. Now we can just repeat this exercise for the y component, and it will again turn out to be the same. We always have the y components of the forces will again be just pointing in opposite directions, and they will have the same magnitude. Now this number, the change in the momentum, delta p, which we wrote as f times delta t. If f is constant, or if f is not constant, we can write it as ft dt from the initial time to the final time. This is what we call, well, sometimes they use the J, sometimes they use I. This is the impulse. Now for such forces where, in this example, the force almost doesn't exist, then the two pucks, they just collide. There is a relatively large force at this instant, and then they just move away. So it's hard to write down how the force changes as a function of time in this example, because it will be just some wild function. It's almost zero everywhere, and it has a large value at a very short interval. So rather than, in such cases, rather than dealing with the forces, we can talk about the impulses given to the object. So since the duration of the force is very short, during this time the objects practically do not move. The only thing that changes is their momentum. At one instant they have one momentum, at the next instant they have a different momentum. Of course, assuming that this collision time is very small. In that case, it will be only this impulse that's what will be important for us. This is just a definition that you will see.
Before you do the equation, we get one equation, we found the open two on both sides, and then you say that it's conservative.
No, what we found here is we calculated the average forces acting on A and acting on B.
But if not, it is like, for example, 0.198.
Okay?
It's pretty close to 0.2, but it's not.
That can never be.
So our assumption should be to the 0.2 of the equation.
No, you see, there are two things. One is the laws. Okay, for example, Newton's third law tells me that they cannot be almost equal. They have to be exactly equal. The second thing is the determination. How do we measure it? Here we had made a measurement. And in this measurement at this, it just turned out to be exactly the same. But for example, I ignored some precise numbers. Instead of 0.67, I wrote 0.7. We could just put in the more precise numbers, and in such a case, this might turn out to be 0.18. The other one might turn out to be 0.22, for example. If this happens, though, the problem here, a more precise, a more correct derivation would be taking into account the error bars. You see, here I have large error bars. The velocities, these are quite huge. This is in the final velocity, there's a 50% error bar. In the initial velocity, there's like a 10% error bar. Of course, those errors you have to transfer into they will cause error bars in determining the momentum of the particle. And since I have error bars in determining the momentum of the particle before and after, I will have error bars in determining the change in the momentum of the particle. And those error bars will not be small. I would expect some error bars of the order of 0.1. So this should be 0.2 plus minus 0.1. The other one can be, for example, 0.25 plus minus 0.1. The central values are different, but nevertheless, within error bars, they are equal, the magnitudes. And they have to be equal. If you make an experiment and you see that they are definitely different, even taking into account the error bars, then you have proven that the Newton's third law is not valid. And we don't have any such measurement.
Thank you. Exactly my question related. If they are not equal, and what are the other components? First, I don't know. What should I think?
Error bars. You should first make sure that your error bars are correct. You have to first study your error bars. Do they make sense? You don't always know your error bars, by the way. Some of the errors you cannot just measure, determine. Now, for example, such things do happen. For example, one experiment just measures one parameter, I don't know, in the US. Another experiment measures another parameter in Europe, and they might differ. But almost all the time what happens is when they improve their experiments, they just come together. They agree on the value. Now, another possible source of error bar is, for example, you go and drop this, measure its acceleration. I come here and drop it from here and measure its acceleration. We should both get something around 9.8. If you measure something wrong, if you measure something differently, then we should first make sure that we are both analyzing our error bars correctly, and we are also measuring the same thing. We have to make sure that we are calibrating our instruments correctly. Any other questions? Yes. Now, in the inelastic case, we have 4 unknowns and 4 equations. In the elastic case, we have only 3 equations. Now, in that case, if you want to find the final velocities of the object, you have to have one more information. Now, for example, you should measure the direction of one of the particles. No. Just by looking at the conservation of momentum and the conservation of the kinetic energy, we cannot determine which way they will go. Of course, if you know how they interact, for example, if your objects are just solid objects, then we know that they just basically reflect like a mirror, as if there was a mirror. So that is, yeah, the angle of incidence has to be equal to the angle of reflection. That is an additional information, though. In this case, just the conservation of momentum doesn't allow us to determine the final velocities. There is either we measure one of the directions of the final particles or their speed, or we have to know something about the forces acting on the system. Other questions? Okay, then see you next week.